Okay, welcome if you're joining us from online or joining us from the future, I guess. We've got a quick question, which is like, which of the formulas for exponential change are ones that I think are more important to focus on? So the main one I want to mention, so this is for exponential change. The main one is just the general form of exponential change. So this general equation and understanding what each part means on a graph, for example, that's the main thing that I would, initially focus on. So if this is my x-axis and this is my t-axis, this this equation tells me that I start at x naught and then decay to some lower value. Oops, there we go. To some lower value. So the other one to know, this is like kind of like level 1 exponential decay. This function always decays to 0 as long as lambda is positive. The other one to know is the finite asymptote. So if this is x and this is t again, and I have a graph that decays to a finite value, let's say it decays up this time instead, just for fun. Boom. So this general form is good. That's a plus b e to the negative lambda t. This x of time is a plus b e to the negative lambda t, where a is the asymptote and b is down here. And I think I might have switched these in the lecture. They're just constants, so it doesn't really matter. Okay, and then the last, I'd say the last two things to know are charging and discharging of a capacitor. I gave explicit formulas for those in the lecture, but they're just two forms of it's just two specific forms of these two general equations. So it's just a particular case of these two. Yeah, so those are the primary equations. In the lecture, I tried to draw like a solid box around the equations that I think of as most important, although it's definitely possible that I missed, one or two. Thanks for your question. Question, what the C stands for? Yes, capacitance. So capacitance in an RC circuit, which again, if you haven't watched the lectures yet, no worries. We're going to pivot off of this and go back to like basic circuits here in just a second. But if you have an RC circuit, so I've got a battery, a resistor, and a capacitor, which is just two plates of metal that are separated by a distance. Capacitance tells me roughly how much charge can be stored on the capacitor. So kind of like how much fluid can be stored in the columns, in the fluid case. In the, we have two fluid columns and there's a connecting pipe between them. Capacitance is kind of like area in that it affects how much total charge I can store, for a given voltage. So the larger the capacitance, the larger my silo. Okay. I think with that, I'll probably go ahead and launch into the, launch into the quiz. I'm planning on doing quiz 2-2, I think. Let me double check myself here. I wrote it down on a note, but I left my note somewhere else. Files, practice quizzes, circuits, 2-2. Double check myself. Yeah, all right. So I'm going to pull this over, and then we can launch in. How'd y'all feel about the quiz? Did it feel like overall more difficult, less difficult? I think overall, yeah, we did around the same as we did on the last quiz, which is, I mean, it's good. I want to try to keep it consistent, like around the same difficulty. And then based on like individual variation and what you thought was like easier, difficult in DL, I'm hoping that shows up accordingly. So that, so that it's clear what to go back and study for the, yeah, okay, good. All right, so we've got some variation. It's good that we have variation. A little more difficult, harder than the last one, same difficulty as usual, in line with the others, good. Okay, fair enough. Yeah, I'm always down to talk about like what went wrong. And I'll be sure to upload these quizzes as practice quizzes sometime soon. That was a recommendation given to me recently. I'm definitely going to do that. So I'll upload those practice quizzes so you can go through them again and, yeah, try to hash out any difficulties. Okay, let us check out this quiz. Everybody see it all right? Cool. So this is one of those, oops, where'd my pen go? Hello? All right, there we go. I'm considering this circuit. I'm supposed to show my work. I've got a battery and 3 resistors. They tell me the amperage of, hang on, they tell me the amperage is passing through these 2 branches. So to just kind of make some marks, when I'm looking at this circuit, the first thing I always think about is, okay, where's the battery? So battery's on the left, it's pointing positive end up. So it's going to try to push current this way. Here's my I. I'm going to call that IB for I battery. Okay, when the battery hits a junction, or when the current hits a junction, it's got to split, or it has the option to split. So I'm going to call this one I1. I'm going to call the one that goes down I2. Okay, so I'm considering the circuit below. I'm supposed to find the value of R. So when I find my value for R, what I'm doing is I'm using my knowledge of the amperages in order to determine what R's got to be. So in particular, let's try this. So I know that the voltage drop across these 2 resistor networks has to be the same. So Kirchhoff's voltage law, or Kirchhoff's voltage law says that around any two loops, the change in voltage is 0. Around any 2 loops, the change in voltage is 0. So that lets me know that, let's draw in some loops. Here's my first loop. I'll call this one L1. Here's my second loop. Call this L2. Have y'all taken anatomy yet for those who are like headed to pre-med careers? Made me think about back pain. Oh, okay. So we've got 2 loops. The voltage drop around each of these loops, the sum of them must be 0. So that tells me that, all right, here I am. Let's start here. I'll work my way around back to the same point. So the change in voltage across the 10 ohm resistor plus the change in voltage across the R ohm resistor. So I'm going to call this one R left and the R right here. Okay. So plus, if I make my way around the rest of the loop, the battery voltage equals 0. Likewise, if I take the second loop, boom, that tells me that the battery voltage plus the change in voltage across the R resistor, the right resistor, is 0. Okay, so let's sub some things in here. The change in voltage across the 10 ohm resistor. Actually, first, let me ask, are there questions about that step? I know at least some of that was required on the quiz, so if there's questions about that, I definitely want that first. Is it clear how I set up those loops?
I just have a question. What is, I think I know the laws, but what is Kirchhoff's voltage law again?
Yeah, Kirchhoff's voltage law is this one. Around any 2 loops, the change in voltage is 0. Or if I, no, you're good.
Okay.
And if I were to write it in mathematical terms, I say the sum of changes in voltage, and then people say subscript loop, although it doesn't really make exact sense. But this is what people say: the change in voltage, the sum of changes in voltage around a loop is 0. So if you're more used to seeing it mathematically, that's Kirchhoff's voltage law.
And then loop rule is different because that's current, or?
Loop rule and voltage law are the same.
Oh, they're the same.
Same
Oh,
thing.
okay.
Yep.
That's what I'm
So this is the same as the loop rule.
Okay.
Kirchhoff's current law. Whoa, can I write down? No, I can't. All right, Kirchhoff's current law is that the currents entering a junction are the same. The sum of currents entering a junction is the same as the sum of currents exiting a junction. So the current loop is the same as the current law. Sorry, current loop. The current law is the same as the junction rule. These ones are same, and these ones are same. Sorry, I know it's a little bit of like a translational shift. I'll try to say junction and loop rule because I know that's what we learned in DL. Thanks, Karen. Riz asks, can we make a third loop with the 3 resistors? Yes, we can. Yeah, you can. So the thing is, it actually ends up being equivalent to what I'm going to show now. And maybe doing the 3 loop resist, like maybe that would actually cut out like an algebraic step. But for me, I always like to loop in the battery. It's just kind of a habit. I think it ends up being algebraically the same though. Like we'll get the same result. The thing is, if you, and this is an aside, so if this doesn't make total sense, don't worry about it. The method previously shown will still work. But if you were to use the 3 loop resistor method, then you would actually have an increase in voltage as you go like the reverse direction across the resistors. So you have to be a little bit careful with your signs if you choose to do this route. So anytime your loop goes against the direction of current, you have to be really careful with your signs as far as whether voltage is increasing or decreasing. And we can talk a little bit more about that in a second if you like. But that's kind of a, yeah, maybe a more like level 3. It's like a level 3 way to look at the problem. I'm just going level 1 or 2 right now. Okay. All right, so I've got these changes. Again, I'm looking for just the value of the resistance, R. So I'm going to plug in some terms. So through the 10-volt resistor, I've got 3 amps of current. So since I've got 3 amps of current through the 10-volt resistor, that means that's -3 times 10 for that first term. Minus, so there's this R resistor, this lower R resistor, that's going to be -3 times R, plus the battery voltage equals 0. Okay, on the lower part, I've got a 4 amp current passing through this R resistor. So it's going to be -4 times R plus the battery voltage is 0. Okay, cool. So this is a system of equations with two unknowns, R and E, but fortunately they both have E in them. So like I can subtract them if you're comfortable with that. There's a few different ways to think about this. What I'm going to say is just like, I'm used to thinking of it as like I subtract this equation from this equation. Another way you could think of it if you like, which will give you the same result, is that both of these are equal to 0. So I could just set them equal to each other and solve back too. So -3 times 10 minus 3 times R plus E equals -4 times R plus E. So either way, you end up with the same algebraic result. For me, I just see these two E's and I like to subtract. So that's how I'll solve it. But solve this as you choose. And we're going to get rid of that E. We're going to get rid of that battery voltage. So I'm going to subtract away the lower equation from the upper equation, which constitutes just doing the same thing to both sides. So that's -30 minus 3R plus E, there's my top equation, plus 4R minus E equals 0. So battery voltage goes away. I'm left with -30 plus R equals 0. Sick. 30. And the units of resistance are ohms. So R equals 30 ohms. Okay, intuition check. Intuition check. Does that make sense? If I were to have a 30 ohm resistor over here, oops, let's write it in a different color. It's getting messy. if I were to have a 30 ohm resistor down here and a 30 ohm resistor over here, would I expect the kinds of currents that I see? They're the same R. Good question. These R's are the same value of R. Yeah, they refer to two different resistors, but they are the same value resistor. So they're two identical resistors. Okay, so I've got one branch here that has 40 ohms total and one branch that has 30 ohms. I see that the current through the 40 ohm branch is 3 amps, and the current through the and the current through the, what do you call this thing? The current through the 30 ohm branch is 4 amps. So 3 amps through the 40 ohms, 4 amps through the 30 ohms, which makes sense to me in this, like, because the one that has more resistance, I would expect to see less current in. That's my intuition check at the end. So I finished the problem. I just kind of go back and make sure that it physically makes sense. Yep. Okay, so I'm okay with this. If it turns out to be wrong, let me know. But I think it's fine. Okay, so now I'm asked to find the equivalent total resistance of the network. So this is actually a resistor network that the kind of which we've seen in lab. What I want to do is I want to reduce this resistance using series and parallel resistor addition. So I want to think about which sections of my circuit are perfectly in parallel and which sections are perfectly in series. The first thing that I notice is that these two resistors, which I'll highlight in green, are perfectly in series. These two are perfectly in series. I can't immediately combine, say, this resistor and this resistor, because they aren't perfectly in parallel. The tail of the first resistor, even though it matches up with the, even though the tails of these two resistors match, like this point and this point are connected, the heads don't match. The head of this resistor on the right is connected to the head of this other green resistor. So they aren't perfectly in series. Does that make sense? Questions about that? So the reason I care about that is because I want to reduce this first, this left series section first, before I think about adding these two sections in parallel. Okay, so if you're typing, please do continue to type and I'll come back to it, but otherwise I'm going to move on. So this middle section here is two things perfectly in series, a 10 ohm resistor and a 30 ohm resistor. So their equivalent resistance, the R equivalent of just that central section, is 40 ohms. And I'm going to get rid of these loops. They aren't really serving a purpose anymore. Okay. 30 ohms. So the equivalent resistance of these two together is just, in series, we just add things together. So that's just 40 ohms equivalent. Cool. So we've got 40 ohms equivalent on this mega resistor here. And now I've got two resistors that are perfectly in parallel, a 40 ohm resistor and a 30 ohm resistor. So the way I add those up to find the total equivalents are equivalent is I go 1 over R1 plus 1 over R2. So R1 is going to be 40 ohms here. R2 is going to be 30 ohms. 40 ohms plus 1 over 30 ohms. And then I invert the whole thing. Hopefully that formula is looking familiar. So let's do that. 1 over 30 plus 1 over 40 to the negative 1 is 17.14. Not a very pretty number, but we'll take it. Okay, my intuition check. Make sure I've done my math correctly here. So anytime I've got a series or a circuit in parallel, I expect to see a total resistance that is less than the resistance of each individual branch. So 17.14 is less than 40, 17.14 is less than 30. So I feel okay about this. I think this is probably, it's definitely on the right side of the numbers it could possibly be. It's less than 30. Okay. In terms of algebra, so if I were to write this equivalence as just straight up in terms of the variables, if that's how you like to solve problems, which is kind of the cleaner way to do it a lot of the time, then I would say it like this. It's like 1 over R1 plus 1 over R2 plus 1 over R3 to the negative 1, where this one is R1. I'll just label them with numbers. 1 is here, 2 is here, 3 is here. That's the general expression for this circuit. This kind of thing isn't worth memorizing, but you know, it could, if that's how you like to think about circuits, then feel free. Okay, how's the pacing? Y'all want to go a little faster? Are we doing okay right now? Move on to part C here. Feel free to keep typing, like I said. Any questions you have, I'm always down. So now we're supposed to find the voltage of the battery. So to find the voltage, I can just straight up use one of these equations that I've already written. So I will. So I now know that R is just 30. So I'm going to use Kirchhoff's voltage law. That's what I did to get one of these equations. I'm going to use Kirchhoff's voltage law and the knowledge that R is 30 to find the battery voltage. So negative 3 times 10 minus 3 times, it's not R anymore, now I know what it is, 30, plus battery voltage is 0. So what is that? It's going to be negative 30 minus 90 plus equals 0. Oh, this is very cute. All right, so we got a 120 volt battery. Yay. Just like the walls. Not really. Okay, 120 volts is our battery voltage. Okay, again, I can do an intuition check. If I look at my branches, the change in voltage around one of the branches is going to be 0. So how much current would I expect to flow through a 30 ohm resistance? Well, I'd expect 4 amps to flow through it if it's 120 volts, right? Delta V equals negative IR. And that is equivalent to thinking about it just from the equation. They're identical. Okay, so that's it for question 1. Question 2, this one's maybe a little bit more like theoretically interesting. This is kind of just cranking through some resistor addition.
Can I ask a question actually
Go
about
for
the
it.
first part A?
Yeah.
Just generally, like, how would you know to take that approach to find R?
Sure. So if you aren't sure in general where to start on a circuits problem, Kirchhoff's voltage law and Kirchhoff's current law are the way to go.
Okay.
Kirchhoff's, like if you're willing to do a complicated enough math, Kirchhoff's voltage law and Kirchhoff's current law can be used to solve any circuit, meaning you can find the resistors that are, how do I say this better? You can use them to solve any circuit in the sense that if you know enough about your circuit, you can find out everything else. So if I know all the resistances and all the batteries, I can find the currents throughout my circuit if I use Kirchhoff's voltage law and Kirchhoff's current law, or the loop rule and the junction rule. So as a first jumping off point, trying to make those equations and looking at what variables are present can help you figure out if they'll help you solve the problem or which loops to use in order to solve the problem.
Okay.
So here,
And then oh, sorry.
yeah, go ahead. No,
I
no.
would just guess like the more problems you solve, the quicker it comes to like.
Yeah, I think the quicker you come at seeing like which expressions are going to be most useful to you. So like here, say that I had taken just one of the loops. So say that I'd taken just this loop. Well, then I would have ended up with, this equation. That equation has 2 unknowns. It has an R and an E, right? So, so since it has 2 unknowns, I know that I need more information because one unknown, is all I can solve for. Like if I know a function that has only one unknown, I can just solve back for the unknown. But if I have 2, then I need another equation. So I knew I had to make another loop. That's maybe how I would describe it procedurally. Does that help?
Yeah, that's very helpful. Thank you.
Yeah, sure thing. Cool. And was there a follow-up to that? Or was that it for now?
I'm good for that.
Okay. Cool. Thanks, Karen. All right. Bulbs A, B, and C in the circuit below are all identical and all glowing. Rank in order from most to least the brightness of the three bulbs. Explain. So there are a few things to think about here. The first is when we talk about the brightness in three bulbs, what we're really talking about is power. So power is current times change in voltage. This is the power dissipated in any element of a circuit. The power dissipated in any element of a circuit or any section of a circuit. So for example, I can talk about the power dissipated just in A, or I can talk about the power dissipated in this whole network of what do you call these, bulbs, by knowing the change in voltage from the ends and the amount of current entering the area. So I can calculate individual powers, but I can also calculate like powers of the whole circuit. Here, we're looking at it on the individual level. We're supposed to rank in order from most to least the brightness of the three bulbs. So let's think about what's going on in this circuit. I've found my battery, nice. So I've got current that's flowing this direction, clockwise. So current is going to enter battery A. I'm going to call this I1. Current then has the option to split at this junction into either I2 or I3. So I know from Kirchhoff's current law or the junction rule that I1 equals I2 plus I3. Also, am I back to green yet? Has my camera turned green yet, or am I good? So far, typical. Oh, nice. I'm cured. Okay. Okay, so I1 is I2 plus I3. So the current splits at that junction. That means that some of the current goes into the B battery, or not the B battery, the B bulb, and some of it goes into the C bulb. And these two bulbs are identical. So just from looking at it, I don't expect that there will be a difference in their brightnesses. A more rigorous way to think about why I don't think there's going to be a difference in the bulb brightness for B and C is if I think about the voltage drop delta V across either bulb, I expect both of those to be the same. So another way to write power using Ohm's law, so if I use Ohm's law on this, which is delta V equals IR, and I substitute in delta V over R for I find that power is delta V squared over R. So since I have the same change in voltage for these two resistors, or for these two bulbs, and because they're identical and they have the same resistance, that means the power dissipated by bulbs B and C are the same. So I'm going to write down here because I've been using a bunch of the rest of the problem to demonstrate some more technical stuff. So B and C are equally bright. I'm going to type this because my handwriting is illegible this morning. Since B and C both have the same voltage drop and same resistance, and since power can be written as delta V squared over R. And I'll make that big enough that it's actually legible. There we go. Equally bright since B and C both have the same voltage drop and the same resistance, and since power can be written as delta V squared over R for any individual element of the circuit. Okay, so the last one to talk about is A. Rank in order from, or sorry, what am I doing? That's part A. A is this bulb up here. There we go. So what's going on with A? A has both I2 and I3 flowing through it. So it's got more current flowing through it than either B or C. So since power can also be written as, let's write it another way. Power can also be written as I squared R. So that's applying Kirchhoff's voltage law to delta V. So I'm plugging in IR for delta V here to get I times R, I squared R. Since power can be written as I squared R, I see that A is receiving more current than either B or C. So since A is receiving more current, I'm going to type this too, more current than identical bulbs B and C, A is brighter than B or C. Okay, so A is getting more current, and because its power is larger than B or C individually, it is brighter than B or C. Okay, questions on A? Feeling all right about power?
If light bulb A was after B and C, would it still be like have a higher power?
Yeah, good. So moving A to, like if I were to move A, say that I connected this section by a battery here, let's just be super clear about what I mean. So say that I connected it here with just a thick, an apparently very thick wire instead, and then I moved the A bulb over here. So it would still be receiving the same current as it was up here. So the currents recombine, I2 and I3 recombine at this junction to make I1, the same current that it was making before exiting the battery. So moving the bulb to a different position where it's still in series with this section gives the same brightness. Good question, Jordan. Does that make sense? Like why it is? Or still a little fuzzy? I can explain it a couple different ways too.
Yeah, I get it.
Okay, good stuff. So yeah, the specific location of A doesn't really matter as long as it's not placed in parallel with these guys. So like if I put A right here, okay, well now it's in series with C, right? So now it's like I've fundamentally changed the structure of my circuit. Or if I were to put A over here, now it's in parallel with B and C. So again, I've changed the fundamental structure of my circuit. But if I just put it in series with this BC section, then my circuit is essentially the same, mathematically equivalent. It reduces the same way. Good question. Okay. Suppose the wire is connected between points 1 and 2. Nice. Everybody loves doing these short questions, short circuiting questions. So I'm connecting a wire between points 1 and 2. What happens to each bulb? Do they get brighter, stay the same, go dimmer, or go out? So here's C. I'm just connecting these by a wire now. So we talked about shorts, I want to say 2 times ago, and maybe briefly in the last problem solving session, but I know that one was a little harder to access. So, so the deal with a short like this is because any 2 points connected by a wire must be at the same voltage, that means that the change in voltage across this point 1, 2, now that I'm connected by a wire, is 0. So the change in voltage between those 2 points is now 0. So what does that mean for B? Well, let's look at B first. So these 2 points are essentially just the same as points 1 and 2 in terms of their voltage. So the change in voltage across B is now 0. For A, A is connected directly by points 1 and 2, so the change in voltage across A is also 0. Finally, or sorry, that's not A, that's C, my fault. Verbal typo. The voltage across C is 0. Okay, finally we have A. So A now absorbs the entire battery voltage. Delta V A is the battery voltage. Why is that? Well, I'm going to change colors here. A is now connected by a wire to the negative terminal of the battery and to the positive terminal of the battery. So A now absorbs the entire battery voltage, whereas before it had to share, it had to split it with B and C, because B and C are in B. The BC circuit here is in series with A, the A resistor. So A is going to get brighter because it's now receiving more voltage for the same resistance. A is brighter as P power is delta V squared over R, and delta V A increases. All right, let me go ahead and just type that too, because I know that's not good. Not very visible. Okay, A is brighter as P equals delta V squared over R, and delta VA increases. Okay, hopefully that's legible. All right, B and C both go out because they have no voltage across them. So B and C go out as delta V B equals delta VC equals 0. So there's no power being dissipated within them. I can think of this also in terms of current. So what I'm saying now is that all current diverts through the short. So all current goes around B and C. It doesn't want to go the path that includes resistance if it can take one that has 0 resistance. So all current passes through this little shortcut here, this short. And because there's overall less resistance on the battery, a greater current is traveling. So a greater current is traveling through A as well. That all lines up, hopefully. Okay, more questions on this guy? So we've still got around 15 minutes. I'm down to do another circuit problem, or we could do like something on exponential change for those who are interested in exponential change. Can I make a quick poll here and ask? Add a question. All right, this might not, okay, here we go. What next? So also, if you have questions you want to talk about, quiz questions or just questions from DL, feel free to put those in here. So quick exponential change. All right, let me know what you think. Okay, it looks like we're overwhelmingly interested in exponential change. Question also, wasn't able to take the quiz, how'd that work? So feel free to follow up with me about this. Let me know, like I assume it was the power outage, right? Please do send me an email if you had the power outage. The goal of the 2 dropped quizzes is to act as a buffer against technical difficulties. I know it's not quite like completely fair in the sense that students who are able to take the quiz ultimately have like more shots and can get more drops out of it. But we're trying to minimize the impact of these kinds of things. That said, it's hard for us to give the quiz at a later date because multiple choice quizzes the answers tend to leak out pretty easily. So please do send me a follow-up message though, because especially for students who have like more than 3 technical difficulties, I really want to be sure that we can accommodate that. Or more than 2 technical difficulties. Okay, so let's hit an exponential change one. Let's just pick a random one. Let's do this. Whoa. I'm going to get this a little bigger. Okay, I'm going to go through this one fast. Next week's is also planned to be an exponential change problem. So we can go through it a little bit faster at that, or a little bit longer at that point, I guess. Yeah, take a little more time there. For now, let's take a quick look. I've got two identical standpipes connected by a thinner pipe sitting on your DL table in an equilibrium state with equal water levels of 10 centimeters in each pipe. Suddenly, you lift one of the water types by 4 centimeters as depicted here, defined as the state at t equals 0 seconds. On the plot provided below, plot the height top of the water level as a function of time for each standpipe measured from the bottom of each container. Clearly label curves and indicate the initial and final height values for each pipe. Show your work and explain your answer. Okay, cool. So I've initially, one sec. I've initially lifted my pipes by 4 centimeters. So the original delta H, the original difference in height between the two levels is going to be 4 centimeters. So I expect that at the end, the two will, this upper one is going to drop 2 centimeters, and this lower one is going to raise 2 centimeters relative to its base level. So yeah, measure from the bottom of each container. Cool. So initially, they're each at 10 centimeters. So I'll mark, how about this? I'll make this one red. I'll make this one orange. So the one that is at 10 centimeters on the left is going to drop down to 8. So here's 10. It is going to drop down. Whoa. Hello. It's going to make a nice little decay to this asymptote at 8 centimeters. The one on top starts at 10. It's going to go up to 12. It's going to increase by 2. So we're going to have the same decay rate. So I want to draw, it's going to be kind of like a parabola twisted on its side, but it's got a little kink here at the origin, or at t equals 0. Here we go. At this point, it's got a little kink in it. So it's not, this is not a parabolic curve flipped on its side, but it's 2 exponentials. Okay, clear label curves. My labeling is close enough. So indicate initial and final height values for each pipe. Show your work, explain your answer. Centimeters. So I don't think at this point they really want me to, I don't think they're going to want me to indicate what the half-lives are. Because I don't have the resistance. So I'm just going to leave my time axis unlabeled. As a reminder, how do we know it asymptotes to 12 and 8? Okay, I've got a question coming in. Let's address this. How do we know it asymptotes to 12 and 8? So the asymptote describes the equilibrium height of the final setup. So to draw this picture a little bit more accurately, here we go. Here is 10, which means 4 would be about this tall. So let's draw another one. Cool, there's my 2 containers. Here's around 4. Okay, so this one has been elevated by 4 centimeters. These 2 water heights then are going to be 4 centimeters apart. So I'm measuring each height relative to the base of each tank. So I'm measuring each height relative to the base of each tank. So this upper one is going to drop down 2 centimeters to meet the other one, which has risen 2 centimeters, or which will rise 2 centimeters. So because they're identical pipes, identical standpipes, they've got the same area. So if one drops by a certain distance, the other one will raise by that distance because the same volume of water is exchanged there. So if there's a total height difference of 4 centimeters, then in order for the water to become level, in order for the system to be at equilibrium, in order for the system to be at equilibrium, in order for the water to be level, one of them will drop 2, the other will increase by 2 to balance out the total difference of 4. Does that help, Jordan? All right, good stuff. Okay, so this is my asymptotes. I'm not expected. It would have been nice to have this communicated more clearly, but I'm not expected for this question to put like how long a half-life is, because the equation for half-life. Oh my goodness. Okay, so there was a question at the very beginning about like which equations are important. Here's another important equation, so I'll write it. So tau is the half-life over natural log 2. Okay, so tau is that thing. 1 over lambda is tau, or 1 over lambda is tau, tau is 1 over lambda. So these are another important set of equations. And lambda is the thing inside the exponent. So I'm not expected to know any of these directly from this problem, because I don't get to know the resistance of the pipe. So the lambda of this fluid system, similar to our other fluid system, is going to have something to do with rho times g and area and resistance. So since I just don't have a lot of these values, I'm not expected to like mark anything on my time axis, because I can't know anything about the half-life with the information given. Okay, does that make some sense, hopefully? So I'm not going to mark my x-axis. What they asked for is just label the curves, indicate initial and final water height values. I'm just going to leave the time axis alone. Okay, question B, or question 2. What is the height of the water level in each container after a time of 2 half-lives? Explain. So 2 half-lives, that's basically what does this mean if I have 2 half-lives? So my first half-life takes me halfway to my asymptote. Did I spell that well? I think I did. And the second one takes me another half. Second takes me another halfway. So if I'm 10 feet from my bedroom door and I go halfway to it, I'm now 5 feet from my bedroom door. If I go halfway again, I'm now 2.5 feet from my bedroom door. So I get 75% of the way there in 2 half-lives, 75% of the way there in 2 half-lives. Each of these pipes travels 2 centimeters, or each of these water levels travels 2 centimeters to get to its equilibrium position. So it's going to travel 75% of 2 centimeters over. Each will move 75% of 2 centimeters. So each of them moves 1.5 centimeters, which is going to take my upper pipe from 10 centimeters down to 8.5 centimeters. So, oof, I know I'm kind of pivoting all over the place here. So for 2, upper pipe, 7.5 cm, 8.5 cm, sorry, 10 minus 1.5. And for my lower pipe, the one that is ground, lower pipe, all right. Probably we should just move on here because it's already at 56. Okay. The resistance of the thin connecting pipe is 2,000 kilogram per cubic meter second. On the plot provided, plot the current through the thin connecting pipe as a function of time. Clearly indicate the initial and final values of the current. Show your work and explain your answer. Tell you what. Let's do this. Okay, so what is current? Current is the rate of change in volume per time. I know that current in general for this system is going to be negative rho g delta y over r for reasons that are outlined in the lecture, I won't go through it right now because we've only got like 3 minutes, but the current in general is going to look something like this. And the change in height is going to look like, or sorry, not rho g delta y over r. No, that's right. Yeah, that's fine. Negative IR, rho g delta y. Yeah, that makes sense. Yeah, I feel okay about that. So it's going to do the same deal. It's going to rho g delta h naught over r. Wow, that's not very pretty. So the initial height difference over r. So it's going to be 1,000 times 9.8 times 4 centimeters divided by r. So 1,000 times 9.8, or we'll say 10 for gravity, times 0.04 meters for the initial difference in height, divided by 2,000. So that'll be our initial point. The final value of current is going to be 0. And then we've got all of our half-lives, which we don't get to know the value of because we don't know the area. I don't think. Double check me here. Yeah, we don't. So we still don't get to know the exact length of a half-life, but we can know the initial current just by knowing the initial height difference. So that's the initial current here. It's going to be 10,000 times 0.04 over 2,000. So that's going to be 0.2 cubic meters per second. Which kind of feels like a lot. Possible I made an error. We should go back and check. Maybe next time. So I think I'm probably going to call it there. I know we've only got about a minute left, so I'm happy to take wrap-up questions. Otherwise, feel free to head out if you're just sticking around for the problem session. Thanks, everybody. There's a question, what is the word after asymptote? Question, what? I'm not sure what the word after asymptote is. I'm sorry. Where are you looking? Oh, okay. 75% to asymptote. There we go. Yeah. What is that? It's supposed to be asymptote. Sorry, Jordan. Thanks, y'all.
I just had a quick question.
Go for it.
Could you explain how you got 8.5 and 11.5 again?
Yeah, sure. So, so each half-life takes me halfway to my goal. So since each of the pipes is going to eventually move 2 centimeters, the upper pipe is going to move down 2 centimeters, the lower pipe is going to move up 2 centimeters, so that the water level can be the same across the 2 pipes relative to like the ground. So in the first half-life, they're each going to move 1 centimeter. So they're each going to be now 1 centimeter away from the asymptote.
Oh, okay.
In the second half-life, they're going to move 0.5 centimeter. So they each move 1.5 centimeters total.
Okay, that makes sense. Yeah.
Nice. Good stuff.
All right, thank you. Have a good day.
Sure thing. Yeah, you too. All right, y'all. I'm actually going to go ahead and wrap up the meeting here. I got to run off to another meeting. But thanks for coming out, and hopefully I'll see you next time. Thanks, folks.